So I'd like all the panelists to come back online if you could. Brian, great, and Jeff. So there are a number of questions, and we cannot get through them all. I think we have about 15 minutes left. So I think what I'd like to do is kind of start with, maybe rather than specific questions, if you could address some of them yourself. I really want to get like a broader perspective. I know, Brian, this isn't your field for, as long as the rest of us, but I think it's useful to have newcomers and old timers answering these questions. So the first question that I really want to address is, what does everybody think is the most pressing need in terms of advancing the DEL technology to a way that it can more quickly produce starting points or drugs for therapeutic use? So maybe I can start with Jeff and then pass it on.
Thanks, Gwen. So, I think, from where I sit, there are kind of two things that sort of nag at me. And, one is we see, and I think a lot of people have seen, this over the years, there's sort of a bimodal response to DEL, sort of the DEL process, if you will. If you look at it as we take a protein target, we try to qualify that target, and you find it either really works, right, or it doesn't work. And you don't know until you've spent a couple months making compounds, right? And there sort of tends to be this kind of, when I say bimodal, right, you might have like a target where your confirmation rate of hits is 75, 80, 90%. And then you'll have another target where your confirmation rate's like 5% or 0%, right? And the average ends up being about 50%. So it's very useful, and it's not a terrible false positive, but I don't think we have a really, really good understanding of how to tell before we kind of invest that chemistry which kind of target you have, right? There are certainly targets where you don't get any sort of meaningful selective results and that you can kind of just pause those, right? But then telling the difference between, those, I think is one of the sort of the big challenges. And, I'd say the other one is it is just a binding assay. And this is what has me so excited about the work Brian's doing, right? His lab in 1859 and other companies, like that, around getting into that, functional space where you can leverage the decoding technology and the throughput and the low reagent usage, that DEL brings, but also kind of dial in that functional bit, do some really interesting mechanistic work, where you just couldn't run full diversity screens, to get at, sort of allosteric mechanisms, right? For kinases, even for well-trodden target space, that sort of thing. So those are kind of the two things I see as kind of the big gaps.
Great. Can I pass it to Brian now? Can you take that same question and add your perspective?
Yeah, actually, I was just going to say it's, I think the next step is for people like me to be able to generate more data to feed the Jeff machine, more and different layers of data. I was really, it's something that impressed upon me when I was visiting Pfizer now many years ago is, they said, we know a lot about every compound in our compound file. We know what targets it hits. We know a lot about its pharmacokinetics, and we know basically nothing about any given DEL compound. And so I've been thinking about ways that we can kind of adapt, kind of maybe as a sidetrack, some of the stuff we've been doing on pharmacodynamics and target-based stuff. Can we kind of start reconstituting some of those same ideas in pharmacokinetic screens so we can get more information about what's in libraries and then begin to parse those out at the design phase? Like, how can we get into really nice space all around, not just what's appropriate for hitting the target, but for also not getting us into kind of a molecular sand trap.
Yeah, thank you. So Ryan, do you want to add to this?
I think from my perspective, what I think is sort of the next wave, and it's already been touched on here, and that is starting to apply it in a cellular context. I think that is that has so much application to jumpstart the next starting at that point, you skip a lot of the steps in between, right? And so I would just bring that to this audience to be thinking about.
Yeah, I guess I would, to conclude that idea, I would echo that a bit. I think, we found getting into the degrader space to be intellectually challenging for us in the beginning because we just weren't sure that we could produce orally bioavailable molecules. But by taking a rapid path to get into cells early before we knew a lot about our compounds, it enabled us to look for the thing that we were looking for, which was protein absence. So if there would be a way to apply, larger sets of compounds in a screening mode that gets you into cells in a sooner fashion, I think it could give you some advantage. I mean, obviously with cost parameters in mind, which means it needs to be miniaturized and it needs to be very robust. So I think that is a big challenge for the field. Not maybe the only one, but certainly an appealing one. Okay, so if we move on to another general question, I think what do you see as kind of a drawback of the way that we're using DEL in the field right now? Do you feel that the community is applying this technology to things that really it is not well suited for? And would you give an example? And I'm going to start with Brian for that.
You're starting with me now? Let me pass for a moment. I need a moment to think.
Okay, Jeff, do you want to take it? Nobody wants to take it.
Well, I mean, I think it's one of the nice things, right, about DELs is accessibility, right? So, in the biotech space, I think, it's a very lightweight way, right? There's a lot of good, sort of quality collaborators, right, in the space, right? And so if you have novel targets, you can get in there, get some hits, and it's a lot less expensive than giving away 30% of your potential profits to a pharma collaborator at the screening stage, or, sort of building out your own screening capability, right? Or, starting from the same information everyone else has. So I think, so I think that's a great use, right? But I think, one of the things that maybe some of the larger companies that are more mature, in this space, I mean, there's a lot you can do outside of sort of hit finding, right? In terms of, sort of kind of coming up with tools and sort of getting into, more chemical biology that I think, is really maybe underutilized by some of the early adopters. But, I think that's possibly an opportunity for, more work and, sort of, to sort of explore, the sort of non-Lipinski space in terms of chemical structures, right? So, if you can come up with, 100 hits that are maybe all non-Lipinski, there's a good chance 2 or 3 of those are going to have sort of interesting cell permeability that you wouldn't have predicted, right? And I think we saw some of that in some of the talks earlier, right, where there was sort of, Nurix actually that you guys have seen, that the space you end up operating in, especially for bifunctionals, right, ends up being new, right? And you need a lot of opportunity there. So I think, there's the push, to really get to 2 cycles of chemistry and get all of your, libraries to be, really good starting points for traditional med chemistry. I think we should leave kind of an 80-20 there and keep 20%, getting into more exploratory space and keep those sort of experiments in the libraries and see what turns up, and be committed as an organization to follow up on them when, it rescues a target, for example, right?
Okay. So Brian, do you want to jump back in, or shall I?
Okay. I have one. I have a mini thought, and that's as far as I can characterize it. And it's not maybe so much like not using the right way. I wonder like why I haven't heard more about DELs on cellularly displayed targets. That feels like something. I don't know if there's just something that, I mean, I'm sure there's something quite a bit difficult about that we're not yet fully appreciating, but that feels like something that should be more like that we should see more of it than we have. And so I would like to see kind of a more thorough kind of diving in on that topic. So that's not misuse. It's just, mini thought. I'm gonna leave it there.
Ryan, do you want to add or?
Yeah, I guess I wouldn't call it, I guess I don't want to comment on misuse. I'm probably not qualified to comment on that. But I would say that something I'm excited about is generating focused libraries. I think we oftentimes think about DELs in the terms of sort of large naive libraries where you're sort of hunting from the first starting point to then development. But I think the use of custom libraries that are focused around initial starting matter and doing that in iterative processes, I think is one of the things I find most exciting about this. As far as maybe one of the challenges, I think it's it oftentimes comes to the follow-up, right? I mean, you can do the initial screens quite quickly, and folks like you all are extremely good at that. But having the capability to quickly move from hits to then validation stage, and how we can do that better, I think is another area for improvement.
Okay, so what I want to do is jump to one of the general questions that we got directly submitted. So it said, with the recent publications from multiple groups, GSK, WuXi, HitGen, Pfizer, that describe the use of on-DNA synthesis to cull false positive hits, it seems that this is a critical improvement in the field, and it also maybe indicates that the data is noisier than maybe we talk about. So I think the real question is the data that noisy? Does it affect machine learning? Is this the way that it should be followed up? What do people have? You can go many ways with that question. So Jeff, I think I'm going to start with you again, because you are the recipient of large data sets that have to be clean enough to give you a prediction.
Yeah, so I mean, I've definitely been chasing what I would call kind of the false positive problem for a while. I'll just put it that way. Maybe longer than most people. I think it's target dependent. So sometimes following up with on-DNA chemistry, right, is really the best thing to do for a target, right? Because it helps you understand, the target better, and for that particular scenario. But in terms of like every process, right? I mean, I think there's something to be said for like a uniform approach, right? Where we do this, we do that. Everyone kind of knows what the next step's going to be, and as long as it meets sort of a trigger point, right? You just sort of move to the next step. And I think a lot of sort of collaborations are set up that way, and so it makes sense in that context. But in sort of the space I live in, I think the on-DNA follow-up is definitely not. It's just delaying the inevitable without DNA, right? And so in a lot of cases, if you have confidence in the outcome, and you're not looking for a bifunctional approach, you're not trying to understand, right, your sort of false positive rate, you just simply move to the off DNA piece. You don't actually follow up on DNA. So I'd say it's target dependent. We tend to deploy it when we're trying to back figure out, like trying to understand why things didn't work out the way we did. But I think if I had to put my money on it, I'd say it's more the protein being in a conformation or having a substantial amount of the protein at that high concentration that you need, right, to sort of drive the interaction in an incompetent state, that we're not, right now in a good place to figure out, what that is and separate it out.
So I guess as a follow-up, do you think that we have the right protein chemistry tools to make sure that particularly novel or less understood proteins are really homogeneous in the way that you're trying to screen them? I think that is very easily answered if it's a well-defined biochemical target, but that's usually not what's going to present problems anyway.
So the simple answer is yes, we have them. But the long answer is they require a fair amount of protein and a huge investment in expertise and time to properly characterize them. And that sort of plays against, I think, the drumbeat of, well, Dell's quick, right? Because you're basically front loading a huge investment in protein characterization, and sort of with it, right? And so I mean, I think where Dell can play there is if you can quickly get some tools to sort of put into the mix that help you even just tease out your protein reagents, and even better, the cellular context that you're looking to go after for some of these new targets, then if you can show that sort of target engagement in the cell, and then in the best case you demonstrate fidelity with the therapeutic hypothesis, then you really short-circuited things and can accelerate. But it's also good to invalidate that, right? Because then you don't invest the rest, because it's a huge investment, right? Because it can do some things really quick, but it doesn't. It's not like a magic protein QC machine. You definitely need that expertise.
Brian or Brian, either one of you want to jump in, comment?
I guess, I mean, I think this is a super important point that, you don't need me to call out, but obviously what the state of the protein you put into the assay is going to dictate what you get back. And that not only means sort of the junk in, junk out, but also you got to think about, what kind of binder or regulator do you want? And, obviously most proteins don't exist in one state. Do you want to have it, bind when it's a monomer versus dimer? And, I think you just have to put in a good bit of thought and characterization of the material, as Jeff was alluding to.
So I want to get one additional question into Brian. I think I think a lot of us are really excited about being able to do bead Dell because it enables you to get into a biochemical assay space that could allow us to take our big collections of binding molecules and also get the secondary readout of a biochemical evaluation. So can you talk about the limitations of being able to grow the library collections large in that space, and what might move the needle eventually to let us use more of our collections for that methodology?
Yeah, so and I think this also gets at your last question too. So unlike kind of affinity Dell, where you do have kind of different binding configurations of your protein target, but what we've been working on now in the lab is looking at the same target but in different modalities. So autotaxin in an activity-based mode, but then also in the fluorescence polarization mode, so that we can get that secondary readout and have more confidence when we see the same hit. And similarly, looking at different libraries where you see the same structure and the same fragment popping up in different modes, that kind of also lends confidence. How to grow the collections, we need to bring our system screening throughput up. We're at 100 droplets per second. And so, it's not as elegant as the parallel selection approach. So we just need to be able to increase, maybe get to the place where like flow cytometers are, in that 10 kilohertz range. And then that will allow us to access kind of the million compound collection, maybe meet somewhere in the middle, not in your bazillions, but maybe in at the million mark or a little bit less.
Well, as we all heard today, the 2-cycle library space, those libraries don't have to be particularly large to cover a lot of the good small molecule space that people want to get at. So I think that, as libraries, the molecular weight of libraries stay small, it becomes more and more amenable to the limitations of some of the screening techniques. So on the panel, is there anything else that I know we've gone over time, but we're all here. So does anybody else on the panel want to pose a question or answer one that you've seen? So if you don't, there's one that was getting a lot of upvotes in the chat. Jeff, do you have any perspective on how long you can really store and get the same performance out of libraries? The comment was around the fact that GSK, being one of the longest purveyors of this, has library collections that certainly would be a decade old if they're still unused. So is there a shelf life?
Well, I mean, it definitely is dependent on the DNA is fine being frozen, right? So the fidelity of the DNA, the frozen DNA is perfectly fine. You know, and it can survive multiple freeze thaw cycles. It's still amplifiable. Qualifying, you know, the reagents, right, hanging off the end of the DNA is a bit trickier. And really the most sensitive way to do it is to have targets with really robust results, right? And then you just recapitulate those. I mean, we have a panel of targets that we'll trot out, you know, as we add new libraries to our pool, and try to understand, you know, because you know, especially as you explore new chemistries, you can get a lot of carry along into the DEL libraries. And so you want to make sure that, you know, by adding the last library that just used that WYSI chemistry, you know, didn't add, you know, some, I always pick on, you know, palladium, right? A little extra palladium that's going to, you know, make your enzymes pretty unhappy pretty quickly, right? And sort of negate, you know, what's going on with the other DELs. So, I mean, I would say, you know, that's probably the best advice I can give, is to sort of set that up. And, you know, there's certainly, we've made libraries, you know, with sort of reactive handles and whatnot. Those definitely do have a shelf life. But, you know, we haven't really seen any evidence of the typical, you know, sort of DEL reactions expiring. Although, you know, I would say, you know, it's not something that we're looking at, you know, on like a quarterly basis. I mean, it's definitely a periodic review.
Yeah. Well, thank you for that answer. And I'm being notified that we have really gone much beyond our time. And I think it's just a testament to how, you know, how interested everybody is in the field, and, you know, how engaging a complex technology like this can be. So I thank you all for your time. I really enjoyed the presentations, and certainly for the entirety of the meeting, it was great. So thank you for your attention. And thank you, Serene and Abigail.
Thank you very much, Gwen. This was an extremely exciting panel discussion session. I learned a lot, and I'm sure everyone in this audience learned a lot too. Okay, so I'm going to close this meeting by thanking all our speakers, organizers, and everyone involved in this workshop. I'm going to thank the attendees. I really hope you all enjoyed the workshop, and I really hope we see you in our future events as well. I hope you check our program websites, and you look at our manual, and, you know, and all these resources that we are providing for you all. And you'll find it beneficial for your research. Also, one more thing I really would like to ask all attendees is to provide feedback. We would love to hear your feedback. What are we doing well, and what we're not doing well, so that we can get better at what we do. So your feedback is extremely valuable. Please fill out the feedback survey that is going to be emailed to you, I think tonight or tomorrow. So you're going to get that email with the feedback survey. I really would like to get your feedback. And if you didn't register and we don't have your email, or if for some reason you're not getting our receiving our reminder emails, please feel free to email Abigail directly. Her email address should have been sent to a message on the Zoom, so you should be able to find it. It was perfect, and she will add you to the distribution list. Okay, so thanks again, everyone, for joining, and I will adjourn the meeting. Goodbye.